Namaste, students, and welcome. Have you ever wondered about the chemistry behind everyday things? Like why soap works or what makes vinegar such a good preservative? Well, today we are going to explore a topic that is at the heart of all these products, carboxylic acids. So let's begin with a simple question from your own kitchen. This one observation will help us understand the special properties of an entire family of very important organic compounds. You see, the secret to the vinegar, and so many other things, is a particular arrangement of atoms called the carboxyl group. This functional group is really the main character today. If you understand its structure, you will understand all of its uses. So let's take a closer look. To make it simple, let's break down this group into two parts which you may already know. You can think of it like a hybrid. The first part is something called a carbonyl group. That's a carbon atom with a double bond to an oxygen atom. And now, on that very same carbon atom, we attach the second part, a hydroxyl group, which you know as the OH group. Now, when these two groups come together on a single carbon, they create something totally new, with very powerful properties. So, a carbonyl and a hydroxyl on the same carbon together form the carboxyl group, which we simply write as COOH. Remember, it is this unique combination that is the source of all the properties we are going to discuss. Now, for your examinations, this is the formal definition you should know. It says that these are weakly acidic because of resonance stabilization of its conjugate base. Now, I know these words can seem a bit heavy, but the main idea is actually very simple. It's all about stability. Let's understand what that means. So, to understand why vinegar preserves pickles or how these compounds are used to make soaps and even perfumes, we have to first understand what makes them acidic. Where does this acidic nature come from? Now, a very common point of confusion for students is to compare carboxylic acids with alcohols. You might think, both have an OH group, so they should be similar, no? But they are very different. Look here. When an alcohol loses its proton, the negative charge is stuck on just one oxygen atom. This makes it very, very unstable. But when a carboxylic acid loses its proton, that negative charge gets to be shared between two oxygen atoms. And this idea of stability is the most important concept to grasp. Just imagine two people sharing a heavy load versus one person trying to carry it all alone. Obviously, sharing makes the situation much more stable. That is exactly what is happening with the negative charge here. It is not a burden for one atom, it is a shared responsibility. And this sharing makes the resulting ion very stable. Let's just picture this process in 3 simple steps. First, the acid easily gives away its proton, the H+ ion. Second, this leaves behind a negative charge on the molecule, forming what we call a carboxylate ion. And third, and this is the most crucial step, that negative charge doesn't just sit there. It immediately spreads itself out, sharing the load between both of the oxygen atoms. This special kind of sharing, the spreading out of the charge, has a name. We call it resonance. And this resonance is the true source of the stability. Because the product that is formed, the carboxylate ion, is so stable, the original acid is actually quite willing to give away its proton. And now we can finally connect this deep chemical idea all the way back to our everyday life. This stable acidity is the secret behind not just preserving pickles, but a huge number of other applications. You see, this microscopic property of resonance stability leads directly to things we observe every day. The sour taste of vinegar, the acetic acid, is because it is releasing those H+ ions. That same acidity, as we see with benzoic acid, is what stops bacteria and fungi from growing in our packaged foods. But it's not just about food. In industry, long-chain carboxylic acids are the main ingredient for making soaps, and when you react them with alcohols, you get sweet-smelling compounds called esters, which create the fruity smells in our perfumes and food flavorings. So let's just come back to that comparison with alcohols one last time. It's very important to understand just how huge the difference in acidity is. We already know the reason, it's resonance, but now let's look at the numbers to really appreciate it. The difference is just massive. A carboxylic acid is about 100 billion times more acidic than an alcohol. It's not a small difference at all. It's enormous. And the reason, as we have learned, is very simple. Alcohols cannot form that stable, resonance-stabilized ion. No sharing means no stability, and therefore, almost no acidity. Okay, so let's quickly summarize the most important points from our discussion today. If you remember these points, you will do very well. First, remember the core idea about the structure. The carboxyl group is a special hybrid, a combination of a carbonyl and a hydroxyl group attached to the same carbon atom. Second, remember the key concept that explains why it is acidic. It is all because of resonance. The negative charge gets shared between two oxygens, which makes the conjugate base incredibly stable. And third, always connect the concept to a real-world example. The stability we just talked about is the direct reason why acetic acid in vinegar can be used as a food preservative. This is a perfect example of how molecular structure determines real-world function. So please, I want you all to remember this. If you can just hold on to the core idea of the hybrid structure, the mental picture of the charge being shared, and one simple example like vinegar, then this topic will become very easy for you. So always keep your curiosity alive. Chemistry is happening all around you in everything you see and use. Thank you for watching. I hope this explainer has helped you to understand the fascinating and very useful world of carboxylic acids.